Do you like electricity but don't want to be bothered with annoying details like extension cables or energy efficiency? Well, good news. In this video, we'll be talking about wireless power, and I'll be testing the limits of its transmission range. With the exception of extremely high energy phenomena like lightning or leakage current through extraordinarily strong electric fields, wireless power transfer pretty much always requires alternating current to work. There's two main modes of transmission: capacitive coupling and inductive coupling. Capacitive coupling happens due to the small amount of capacitance between a transmitter and a receiver, where they act like parallel plates of a capacitor with the air or vacuum in between acting as the dielectric. This is usually a really tiny amount of capacitance, like picofarads or even fractions of a picofarad. Under most circumstances, it's totally inconsequential. But remember, even the smallest amount of capacitance will allow some alternating current to get through. The more capacitance there is, and/or the higher the frequency of the alternating current, the lower the impedance, meaning more power can be moved. For example, let's say this transmitter and receiver have 1 picofarad between them, and the transmitter frequency is 200,000 Hz. That makes the impedance almost 1 megaohm, so not much is going to get through. But when you have something like a Tesla coil, which is producing hundreds of thousands or even millions of volts at frequencies of hundreds of kilohertz, it becomes possible to move large amounts of energy, albeit spread out over a very wide area. This also works with high voltage power lines, although at 60 Hz there's a lot less coupling. Despite that, it's still enough voltage to light up a fluorescent bulb if you stand underneath one. This was Tesla's original vision for power transmission, and while it is a really cool idea that does work, it's pretty inefficient and almost completely eliminates the possibility of radio communication. The other type of wireless power transmission happens through inductive coupling, which basically means the transmitter and receiver effectively become the primary and secondary coils of a big transformer, and energy is transferred through the constantly changing magnetic flux of the alternating current. This approach tends to have a shorter range for reasons I'll explain later, but in my opinion it's a lot more practical and convenient to implement, mostly because you don't need to worry about grounding. See, with capacitive coupling, to get the best result, you want your transmitter and receiver to have the same ground reference, but because inductive coupling is magnetic, the grounding doesn't matter at all. Okay, to get started, we'll need a coil of wire and a circuit to generate some high-frequency alternating current through that coil. Let's start with one of the simplest types of oscillator circuits. This one actually has 2 coils, but only one is used for transmitting power. The other one is a feedback loop that's wired to the opposite polarity of the transmitter loop, and that's what provides base current to the transistor to keep the cycle going. Some schematics may also show this as a single coil that's center tapped, but either way is valid. The circuit is based on the humble joule theif, so named because it can keep sucking energy out of a single AA battery even after it's effectively dead, which happens at about 1 volt. That's because the oscillator will work as low as about 0.5 volts, or whatever the turn-on threshold of that particular transistor is. This is also the type of circuit used to charge the high voltage capacitor on an electric fly swatter, taking in around 3 volts from a pair of AA batteries and boosting it up to 2,000 or 3,000 volts. In my case, I'll be using 9 volts of input, and the diode here will be replaced with a capacitor to adjust the oscillation frequency. For the coil, I used a pair of 5-inch or 13 centimeter diameter coils with 25 turns of 22 gauge wire. Now in reality, the feedback coil probably only needs to be 1 or 2 turns, but it was easier to keep track of what I was doing this way, I guess. As soon as I hook up the 9 volt battery, it comes to life, and thanks to resonance, it's actually getting a negative peak voltage of almost 28 volts across the coil. Next, I made an identical coil to use as a receiver and hooked it up to the scope. Looks like it's alive too, with about 11 volts peak across the coil when it's right on top of the transmitter. Perfect. The bad news is that the power falls off pretty rapidly, and by about 6 inches or 15 centimeters of distance, there's not enough voltage across the coil to light an LED. By knowing the transmitter frequency and inductance of the receiver coil, I can put just the right amount of capacitance in series with it to make it resonate, which can boost the voltage by several orders of magnitude. This allows the transmitter to transfer much more power to the receiver despite being very loosely coupled to it. So now when I measure the voltage across the coil at that same distance, I get around 6 to 7 volts peak, which is around 10 times what I had before at the same distance without the resonant cap. I'll add a pair of LEDs in parallel with the resonant capacitor, and now the transmitter illuminates the lights at a distance of 6 to 8 inches or 15 to 20 centimeters. Pretty good considering the transmitter doesn't even consume 1 watt of power at 9 volts. And here's the circuit running all the way down to half a volt and still getting an output, which is pretty impressive. This thing draws so little current and runs at such a low voltage that you could probably power it off of a lemon battery. I don't have any lemons, but I guess an orange is pretty close. Let's try this. I got a sheet of copper, a sheet of zinc, stuck them in the orange, and there's some voltage. I got the negative and positive backwards though. Let's try it on the transmitter. Sure enough, the circuit powers right up, and while the output obviously isn't very big, it's running stable even with the orange battery being pulled down to 0.6 volts. It's certainly no Tesla battery, but hey, at least I don't lie about the battery range. Okay, so that was about the simplest, easiest wireless power circuit I can think of. It's fun to play with, but I don't really think it has much use aside from toys or middle school science fair projects. Let's try something with a little more power. This next circuit is the ZVS or zero voltage switching driver. This is also a self-oscillating circuit, but doesn't require a feedback coil. The ZVS driver oscillates at the resonant frequency of the circuit's inductor and capacitor, and for reasons I don't completely understand the math behind, always seems to generate a peak voltage of about 3 times the input voltage. Now these do have some limitations. First, the MOSFETs and diodes need to be able to handle at least 3 times the input voltage I mentioned, although I like to spec them for 6 to 10 times just to be safe. I also haven't been able to run them with an inductive load under 0.5 microhenries or over 50 microhenries. And with the resonant capacitors, I haven't had stable results under around 100 nanofarads or over about 2 microfarads. Also, the resonant capacitors need to be very, very low ESR film capacitors because the AC current is very high. But within those parameters, this circuit is amazing, and it can be upwards of 95% efficient if it's built right. This is pretty much my go-to circuit anytime I need to drive a transformer, but I've also used it for induction heating. But in this case, the inductive load will be the wireless power transmitter coil. The coil will be 3 loops of 14 gauge wire with a 12-inch or about 30 centimeter diameter. The circuit draws pretty modest power when it's unloaded, and the FETs won't even get warm. One more thing I should mention is that you have to hard start this circuit, so to speak, meaning you don't want to connect it and gradually increase the voltage from 0. It needs to immediately be connected to the voltage you're expecting to run at. So if you're going to integrate this into some kind of automated system that turns the driver on and off, you'd really want to do it with a relay. Now there are more complex versions that use gate drivers, and those could be turned on and off instead of the supply voltage, but that's a topic for another time. Okay, so here's my test setup. I've got the ZVS driver with the transmit coil over on the left, and the red coil on the right is the receiver. It's got 10 turns of 22 gauge wire and series capacitors to make it resonate at the transmitter's frequency. From about 3 feet or a little under 1 meter away, I've got 5.4 volts peak on the receiver, so we're already doing way better than the previous circuit did. And as you might expect, when I move the receiver closer to the transmitter, the voltage on it goes up. You can also see the current on the ZVS driver go up, since the closer receiver puts more of a load on the transmitter. Let's add an LED. It starts to come on at 5 feet or about 1.5 meters, and with the coils oriented vertically, it's closer to 6 feet or just under 2 meters. To give you some idea of the open circuit voltage that the receiver can generate when it's resonated, I've disconnected the LEDs and put a rectifier and capacitor across the coil instead, and of course a bleed resistor for safety. It charges the cap up to 100 volts without really even trying. That's pretty cool. A smaller receiver coil works fine too, but it has a much shorter range even when it's tuned to be resonant. You can see it also causes much less draw from the power supply on the transmit side. On the flip side, a much larger loop works from much further away. This 30-inch or 0.75 meter coil turns on the LEDs from the other side of the room. This is a distance of about 10 feet or 3 meters. Now there's one more interesting phenomenon that happens with wireless power transmission that's also applicable to radio signals. Let's look at that smaller coil again. Here's its maximum range for the LED to start turning on. Now let's set up the larger coil, but without connecting it to anything. The LED on the smaller coil now turns on well beyond its original range, almost on the other side of the room. When I remove the bigger coil, it turns off again. Here's another view where you can clearly see the effect of the bigger coil's presence on the intensity of the smaller coil's LED. Now just to clarify, this effect isn't related to the size of the coils, I just happen to have these particular coils on hand. What's happening here is that when the unconnected coil starts resonating at the frequency of the transmitter, there's actually a pretty significant amount of AC current bouncing back and forth between the coil and its resonant capacitor. This causes the unconnected coil to become a transmitter in and of itself, effectively serving as a sort of passive repeater, which then extends the range of the transmitter. This also works for boosting reception of radio signals. Here I've replaced the resonant capacitors with an adjustable cap that I can dial in from 300 picofarads to nearly 0, which should put me squarely within the AM radio band given the inductance of this large coil. I placed a small handheld radio in the middle of the coil and tilted it sideways so that its AM antenna is in the same plane as the large coil. Now listen to the effect of the radio signal as I dial in the capacitance. So I didn't actually have to tune the radio itself to a particular channel. By tuning the passive receiver to resonance, the resulting magnetic field created a signal that was strong enough for the radio to amplify it to an audible level. This approach is actually pretty common in AM radio receiver circuits, where the receiver antenna that's tuned is actually totally disconnected from the amplifier circuit and simply serves as a passive resonator. However, it typically shares the same ferrous core as the coil connected to the amplifier, so the inductive coupling is pretty strong. Tunable loops like the one I just made are actually sold as commercial products for boosting AM reception, which is a pretty handy device for the 3 people who still listen to AM radio. Wait, a quick word from this video sponsor, me. Don't worry, my legal department has assured me I can sponsor my own video. If you like my content and want to support the channel, join my Patreon and throw your hard-earned money at me. I post videos several days early without the ads, behind-the-scenes content on upcoming projects, and stuff that would probably get me in trouble on YouTube. Sign up today and help me buy my way out of indentured servitude mining asbestos so I can make YouTube videos full-time. That's it. I guess that's the whole ad. So we've talked about some simple self-oscillating circuits for wireless power and passive resonators, but now I want to see just how far we can push this concept. I mentioned before that ZVS drivers resonate such that the peak voltage across the transmit coil is about 3 times the input voltage, but by forcing the circuit to oscillate at the exact frequency we want, that voltage boost can go way higher, which will extend the transmission range. To accomplish this, I'm going to use a half-bridge circuit, which is just 2 MOSFETs that take turns turning on and off, causing an oscillation across the transmit coil. The transmit coil is yet again hooked up to a resonant capacitor, but in this case the inductance of the coil is much higher than what we'd use on the ZVS driver, and the capacitance is much smaller. Alright, let me give you a numerical example here. The inductance of my large coil is about 360 microhenries, and it has a resistance of about 4 ohms. If I want to drive it at some arbitrary frequency, let's say 230 kilohertz, I match it with a 1.3 nanofarad capacitor, and the Q factor comes out to 130. What that means is that if the LC pair is driven exactly at its resonant frequency, the voltage across the coil can be 130 times the input voltage, although with a half bridge, the effective input voltage is half, so that would make it 65 times, but that still means you could develop nearly 800 volts across the coil with a 12 volt input. With a 120 volt input, it would be almost 8,000 volts, which is what I'm eventually going to use. Now you may be thinking, wait a second, won't 8,000 volts blow up the MOSFETs? And yes, it absolutely would. But the beauty of this setup is that the voltage on this side of the circuit stays between the input voltage and 0 volts, but the massive resonant voltage swings happen on the other side of the coil where it connects to the capacitor. Now this does mean you need to have a capacitor that can handle high voltages and relatively high currents, but that's not so hard to make by putting lots of small capacitors in series. This is the 1.3 nanofarad capacitor I built by making 2 sets of 50 33 nanofarad capacitors in series and wiring those sets in parallel. The individual capacitors have a very low series resistance and a voltage rating of 630 volts, giving this bank a maximum voltage of 31,500 volts. Now this thing probably isn't going to go over 10,000 volts at resonance, even in a best case, but I like to have that overhead. You may also notice that this capacitor bank looks very similar to those you might find in a spark gap Tesla coil. Now I've got to turn these MOSFETs on and off somehow, and I have a long history of destroying gate driver chips, so I'm going to go with a different approach, which is the gate drive transformer. The cool thing about using a transformer is that it's totally isolated from the voltage supply of the half bridge, so you can run it with a little 12 volt battery or a separate isolated 12 volt supply or whatever else you like. It's on its own little island. The primary side of my gate drive transformer will be center tapped so that I only have to use low side MOSFETs to drive it. These FETs are then driven by a 555 timer and some BJTs as amplifiers, because remember that whole thing I said earlier about blowing up gate drive chips. The frequency can be adjusted between 215 and 235 kilohertz. Here I've got a dummy load hooked up to the output of the gate drive transformer to test it out. These are 2 4.7 nanofarad capacitors with 20 ohm resistors for charging, which should approximately imitate the load from the typical gate capacitance of a large FET that I'll be using. This is what the waveform looks like on the scope for one of the outputs. Very clean, almost square waveform, peaking at just under 19 volts, so the MOSFET should have the lowest resistance it can get without exceeding the max gate voltage. Okay, let's try hooking it up to the half bridge and see how it looks on the scope. I'll just hook up a 2 ohm resistor with a capacitor as a load for starters. Mostly working, but I need to get rid of that high frequency ringing that happens at turn on, so I'll add a 33 nanofarad cap across the half bridge terminals to shunt that noise to ground. Still a little wavy, but much better. Definitely passable now. This is exactly how the output of the half bridge should look, a square wave with the output between VCC and 0 volts. Meanwhile, the capacitor hovers right at around 6 volts, or half the input voltage, meaning the effective voltage across the resistive load is a square wave with a magnitude of VCC over 2. Now that we know it works, let's hook it up to the big coil and high voltage capacitor and see if it'll resonate when I dial in the frequency just right. Well, it definitely resonates. Problem is, the voltage goes so high it's out of range for my scope. I'm going to put a 50-to-1 voltage divider between the capacitor and ground and then measure at the junction. Looks like it peaks at 10.6 volts, so multiplying that 50-to-1 ratio gives us 530 volts, which is a Q factor of 44. Not quite the 65 I estimated, but it's pretty much working according to plan. Let's see if the transmission range is any different with this improved setup. I built a second coil as a receiver, although it's not exactly the same size because I ran out of wood for the arms. Close enough though. Then, like before, I added just the right capacitance to make it resonate at the same frequency as the transmitter and got everything set up. From across the room, it's already getting 13 volts peak, so I think I can move this thing quite a bit further out. Now I'm at 19 feet or 5.8 meters, and the LEDs on the receiver coil are still turning on. Here you can see the LED turn on and off as I adjust the frequency of the transmitter, and it goes between being tuned and detuned from the resonant frequency. Now all that was with just 12 volts of input. I want to know what will happen if I rectify my mains power and supply the circuit with 120 volts DC. The MOSFETs in my circuit can handle up to 300 volts, so it shouldn't be a problem to supply the circuit with 120 volts. For this situation, a civilized person would use some sort of switching supply with active power factor correction to isolate and rectify the mains power, but I'm just going to be rectifying straight off of 60 Hz. This isn't the most efficient approach, but the circuit for doing it is pretty simple and harder to accidentally blow up than a switching supply. It consists of 4 components: a bridge rectifier to turn AC to DC, a very large value inductor to snub out inrush current, a very large value capacitor, and a bleed resistor so the capacitor doesn't sit around with 120 volts on it when the circuit is turned off. The large inductor and capacitor act as a low-pass filter to smooth out the 60 Hz ripple, and the inductor helps a little bit with power factor correction so the power company doesn't get angry at me. The inductor is just a microwave transformer with the secondary removed. Here's the whole circuit mounted on a plywood board. We've got the rectifier, inductor, and capacitors for the 120 volt DC supply, and then the half-bridge circuit and the MOSFET driver. On top of the boards, I mounted a pair of fans to keep the FETs cool when the current gets high, and on top of the resonant capacitor bank, I mounted the 12 volt supply. Now the 12 volt supply here is massive overkill, but it was all I had at the moment, and the supply wasn't being used for anything else. Starting off with just the fans and the gate driver, we're pulling about 24 watts. So now I'll turn on the 120 volt DC supply, and we start off at 140 volts with the circuit detuned from resonance. But as I hit the resonant frequency, the power draw peaks at about 330 watts and the DC supply voltage gets pulled down to just under 100 volts. And exactly as planned, the coil is running at thousands of volts when it hits resonance, as you can see from the arcing here. In fact, the voltage and frequency are high enough to light up this fluorescent tube the same way a Tesla coil does, so even though this is meant to transfer power through its magnetic field, the electric field is still really strong. Waving this 3-turn coil a few feet above the transmitter gives over 40 volts open circuit without resonance or anything. With the tuned receiver loop, I'm now all the way down the hall and across the kitchen, which is approximately 40 feet or 12 meters. I walked the receiver back toward the transmitter, but when I got to within about 10 feet or 3 meters, something started hissing. I guess one of the capacitors got too much voltage on it. Placing the coil 20 feet or 6 meters down the hall, I get an open circuit voltage of 13 volts. Here I've connected a 100 kilo ohm resistor. Let's see how far away the transmitter can cook it. Once again about 10 feet or 3 meters, which is the same distance it cooked that resonant capacitor earlier. So the alternating current in the coil has gone up by a factor of nearly 10 compared to the 12 volt test, but I've only got about double the range. Why is that? Well, first off, just like an electric field, the intensity of a magnetic field falls off with distance. But there's yet another problem with the magnetic field from a coil like this. Let's take a cross-section of the coil so we can treat it just like 2 parallel wires that go off into infinity through your screen. When current flows through a wire, you get magnetic field vectors that wrap around the wire tangent to its cross-section. So the field vectors for the wire with current moving away from you would look like this, and the vectors for the wire with current moving toward you would look like this. The intensity of those magnetic fields is given by this equation, which, as you can see, falls off in intensity proportional to the distance. Now, if I'm over here really close to one of the wires, I'm going to feel way more effect from its field than from the opposite wire. But as you get further away, that difference in the effect starts to become negligible, and the fields from the opposing wires almost completely cancel each other out at a certain point. So even if you have tons of current and tons of power, the range you're going to get is going to be limited by the geometry of the transmitter coil, because the relative strength of the magnetic field really boils down to a ratio between the diameter of the coil and the receiver's distance from it. All this math and physics leads to one conclusion: bigger is always better. So we're going to need to build a bigger transmit loop. So I put together this giant wood thing and wired it with 8 turns of 14 gauge wire. The diameter is 15 feet, or about 4.5 meters. It measures 1.5 ohms open circuit, but it'll probably be closer to 3 ohms at several hundred kilohertz. Now we'll hook up some instruments and figure out its inductance by ringing it with this 220 nanofarad cap. Looks like peak amplitude happens at 11.2 kilohertz, which puts the inductance at 918 microhenries. Now my super cheap LC meter thinks it's 820 microhenries, but that thing usually reads about 10% low. I'm going to have to add some trim capacitance to the 555 timer, because to get resonance with my 1.3 nanofarad cap bank, the frequency needs to drop to about 140 kilohertz. Next I add these feet because I don't want the high voltage near the ground and this kickstand thing to stand it up. And just to make sure the base doesn't slide outward, I hammered some rods into the ground to keep the 2x4s in place. Then I hook up the half bridge driver and start it up. A little over 300 watts of power draw once it's dialed into resonance. Inside the garage, I'm already getting nearly 50 volts open circuit on the receiver. To avoid needing to carry the scope around everywhere, I hooked up a diode and capacitor in parallel with the resonant caps to serve as a voltage peak detector, so I can just use my cheap multimeter to figure out what the maximum voltage is based on the distance. Using a tape measure and chalk, I marked out distances from the transmitter in 10-foot or 3-meter increments and then started measuring the voltage. At 130 feet, the open circuit voltage is a little over 2.5, and there's the transmitter all the way over there. Once it got dark, I hooked up an LED, and sure enough, there was enough juice to light it up, although it wasn't very bright. Next, I'll try using a 10 kiloohm load to get some idea of power versus distance. As you'd expect, the voltage across the resistor goes up as I walk closer to the transmitter. Here's a graph showing the voltage with both a 10 kiloohm load and open circuit in relation to distance from the transmitter. The reason the open circuit voltage doesn't have any points closer than 30 feet is because the resonant caps I used were only good for about 100 volts, and then they got cooked when I got closer. Converting these measurements with a 10 kiloohm load to power, we get this graph. Not exactly super impressive, but at 10 feet I could probably charge a phone. Expressing the power in terms of dBm on a logarithmic chart, you can clearly see how rapidly it decays. Almost 50 dB of loss over a span of about 100 feet. Now, seeing the dramatic difference in voltage between the open circuit and 10 kiloohm loads got me wondering what the actual output impedance of the receiver was, since matching the load to the output impedance would give me maximum power. Unfortunately, I'm not fancy enough to have a programmable DC load to sweep through a wide range of resistances, so instead I just got a bunch of different values between 1 kiloohm and 10 megaohms and tried each of them. And just by sheer luck, the 10 kiloohm load I originally picked turned out to be pretty much exactly the output impedance of the receiver. Now, at first I thought this was something I was doing wrong with the data, but turns out I was just really lucky. Alright, well technically it's like 11 or 12 kiloohms, but I was pretty much right on the money with the 10K pick. So as you can probably imagine, having a 10 kiloohm output impedance doesn't exactly make this thing an amazing current source. So for example, when I tried to hook up this nichrome wire to act as an igniter, that experiment went absolutely nowhere. Now keep in mind, all of this is with a half-wave rectifier, but even with a full-wave rectifier, you're not going to get more than a few tens of milliamps. Now of course, we can't talk about wireless power without lighting up some fluorescent tubes, so here you go. Because of the massive voltage boost at resonance, you could get a pretty decent arc from the coil. The problem is, those arcs like to jump between windings, as you can see here. And after a little bit of rain soaked the wood, those thousands of volts found a path to ground and started a fire. Luckily that happened after I finished all my tests, but now I have a giant fire hazard in my yard full of trees. I guess I better take this down before it starts a forest fire, or the FCC shows up.